let's look at steepest descent and newtons and look for kind of some similarities and differences or some parallels. And maybe that can give us ideas for something that takes better steps than steepest descent, but whose steps don't take as long as to compute as Newton's method. So our search direction for steepest descent is the negative gradient. Our search direction for Newton's is negative Hessian inverse times the gradient. So what could we put here to make this formula look more similar to this formula? That's always a good first step. Try to make the formulas look similar and then think about kind of what could be in between those. So think about what to put here to make it look similar to this. Okay, ready? Well, if there's nothing there, that's like multiplying by 1, or for linear algebra, multiplying by the identity matrix. And since we have an inverse here, we could also say identity inverse here. So using the identity and its inverse is easy, but it takes more steps. Using the Hessian and its inverse is harder, but we take fewer steps. We make a bit more progress per step. So we could say a compromise is some matrix which is maybe a little more complicated than the identity, because it's hard to be less complicated than the identity, but not as complicated as the full Hessian. So let's think about what some compromise options are there. Think about it for yourself. All right. So we could say, well, identity is easy to invert because it's a diagonal matrix. What if we just use some other diagonal matrix that would kind of account for whatever scaling the variables? Like if you have one variable that's in meters and another one that's in kilometers, maybe multiply the kilometers by 1,000, then it'll be in the scale of meters, and then they'll have roughly the same scale. So that's basically what automatic scaling does in the Excel solver options. It tries to figure out the scale of each thing to begin with, and then basically tries to rescale all the variables so that the contours aren't so squished. You could say let's rescale and rotate so we don't have to worry about the tiltedness making a difference. You could say, what Hessian should I use? Maybe I'll just take not the full Hessian, but just the diagonal, because that's only n things to evaluate. And that's basically what the AdaGrad algorithm does, but then it includes some learning rate stuff rather than doing a line search. You could just say, let me take the Hessian once at the start of the whole thing and pretend that that's the Hessian the whole time. If the Hessian doesn't change much from location to location, then maybe that's a good idea. Or, and here's the big idea, let's approximate the Hessian as we go along. Instead of evaluating the full Hessian every time, we'll just use information about how the gradient changed from step to step to say what the Hessian is, and that will give us more of a complete picture about the Hessian. So another way to think about it is, we've been computing the gradient, using that as a search direction, or the negative gradient, and then once we get to the new place, we compute a new gradient, and we throw away the information we had about what the gradient used to be, and on the step before that, and the step before that. Doesn't sound like throwing away data is the best idea. So another way to think of it is, the Hessian is the rate of change of the gradient, and we've been thinking about the rate of change by like taking a tiny step in one direction and a tiny step in the other direction, like we usually do to compute derivatives. But we could be thinking about it as, how did the gradient change when I started here, did a full major iteration, and ended up over here? So let's take a look at that. So here, if the black arrow was my original, let's say negative gradient, then I could have said, okay, I'm going to change x1 by a little bit, see what the new gradient is, see it's not quite as steeply sloped, and then come back to the black one and say change x2 by a little bit, see, oh, that's slightly more steeply sloped and maybe a little bit longer, and from that figure out the Hessian right near there. So that's a good way to approximate the Hessian at that one point. But I could say, if I follow this direction, and maybe my line search ends me up here, I compute the new gradient, which will tend to be roughly perpendicular, maybe. And then I can say, how much did the gradient change from here to there? And that's telling me about the approximate Hessian in this whole region, right, rather than that at that one point. And then I go in that direction, and actually, this is maybe my new gradient. I might not go exactly in the direction of that new gradient, but let's say I ended up doing that, and that line search brought me over here, and then here's the new gradient there, or negative gradient, and then I could use that information of how the gradient changed from here to there, and from here to there, and from here to there, to give an approximate Hessian in the whole region. So that is the big advance of quasi-Newton methods, methods that approximate the Hessian using information gained by moving around as we search. So another way to think of that is like drawing secant lines, lines that go clear through a function rather than trying to be tangent. And the most popular quasi-Newton method is called the Bfgs method. It actually estimates the Hessian inverse rather than the Hessian using some clever linear algebra. You can learn more about it at Wikipedia, as always. And it's kind of neat that if n is your number of variables, then the approximate Hessian becomes the exact Hessian if the objective function is exactly quadratic in n steps. And we've said sometimes it's hard to store the entire Hessian, so if you have a limited memory, like not 8 terabytes for a million-dimensional problem, there's something called the limited memory, BFGS, and you can read more about that here.